Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good morning, everyone. How are you today? Thank you very much. So today we are going to discuss the fifth topic, for fundamental chemistry practicum, which is making the pH indicator from natural dyes. Before we start, I would like to ask you about the theory behind the acid-base solution. So we know that there are three types of solutions, which are acid, neutral, and base. And then we have already learned in class before that there are three different theories explaining about acid and base. Anyone wants to explain to me again, about the theory that we know in the class? Anyone want to try? Yes?
Regarding the three kinds of acidities, there are acid, base, and neutral. There are also three theories explaining these topics. The first one will be Arrhenius because it is mentioned. The first one mentioned about the acidities. There are two kinds of acidities, base and acid itself. The acid, any kind of substance is considered as acid when it is dissolved in water. Then it releases H plus ions or hydronium ions. For example, it's hydrochloric acid, chloric acid, and then sulfuric acid. Because it is, when it is dissolved in water, it becomes H plus ions, and it's an ion. For example, in chloric acid, it will be H plus and Cl min, and for H2SO4, we simply dissolve it. It becomes two H plus and one sulfuric acid, sulfur ion or SO4, and then because it is because it's simplicity, and we cannot use the theory any further because there are so many substances in the world that will not produce H plus nor OH min, H minus, if it is dissolved in water. But we can still know the acidity of the matter to support the theory. To support the theory.
Thank you again, Mas Alfian, for the explanation. That's really good. That cover all of the theories that we know about acid and base. So I would like to ask you, again, to remind you, when you are explaining about the acid and base, can you give me the example of the acid and then why you think that is classified as acid? Anyone want to try? Mbak Rahma?
Okay, so the example of acid that I know is like lemon, orange, and also vinegar. While the example of base that I know is like a baking powder. So we can classify that matter as acid and base based on the taste. So we can say that acid has a sour taste, while the base has a bitter taste. Like this.
Thank you very much for the explanation. That's really good. Is it safe for us to taste every single compounds that we do not know to understand whether the compound are acid or base? What do you think? Yes?
I think that's not safe if we taste all of that food or matter. So we need to use the indicators.
Thank you very much. So yes, thank you very much again for the explanation. So we are going to discuss about the pH indicator, to determine whether the compounds are classified as acid or base. But before that, I would like to explain to you about the general introduction of dyes. General introduction of color. So here the slides. Yeah, we can. So here, yeah. Here I would like to give the explanation about general introduction of chemistry of dyes. Yeah. So for compounds to display the colors, they have to fulfill 4 requirements. Yeah. One of them is they have to absorb the light in the visible spectrum. Yeah. And we know that visible spectrum, yeah, range from 400 to 700 nanometer. Yeah. So how do we see the color? Yeah. We see the color when there is a light. Yeah. Touch the matter. Yeah. And then all of the colors, yeah, will be absorbed except the color that is reflected. The color that is reflected is the color that we see. Yeah. That's how we see the color. For example here, yeah, how can we see the blue color? So, for example, there is white light, yeah, white light will be how to say go through the matter, yeah, and then we know that there are a lot of the range of the colors, yeah, from purple here to red there, yeah. All the colors will be absorbed, yeah, in the surface, and then there will be one, yeah, a color that is reflected. For here, yeah, for example, there is one color which is blue color that is reflected by the surface of the matter, yeah. And then because the matters reflect the blue color, and then we can see the blue color. That's how the color works. The second requirement, yeah, the compound should have at least one chromophore. Yeah. What is chromophore? Chromophore is the color bearing group. Here, for example, yeah, alizarin. Here, you can see this is one of the examples of the chromophore. The second one, yeah, the compound should have conjugated double bond. What does it mean? Conjugated double bond means that you have alternating double and single bonds. For example, here, yeah, you have double bond, single bond, double bond, single bonds, yeah, and then that will be used, yeah, for electron to move from one bond to another bond, yeah. So if you have one electron here, yeah, the electron will move here, yeah, through resonance, yeah. That's for requirements for the compounds to display the colors. Another thing, yeah, that can increase, yeah, the color is having auxochromes. Yeah, auxochromes is defined as colors helpers. Yeah, for example, if there is an additional of carboxylic acid, yeah, sulfonic acid, amino, or hydroxyl groups, that will increase the colors. Yeah, that's we call as auxochromes. So we have already understood, yeah, the definition of acid and base. And then we have already discussed, yeah, about the requirements for the compounds to display the colors. And then we will try, yeah, to make our own pH indicator. Yeah. So you are going to be a teacher at school, yeah. And then not all schools, yeah, will provide or will benefit, yeah, to have synthetic pH indicators. Here, you will be prepared to make your own pH indicator by utilizing natural dyes. Yeah, so you can go to the garden, yeah, and then take some flowers or fruits or vegetables, and then extract these colors, and then use that as natural pH indicators. Yeah, this is the things that you can do, yeah, by using the natural dyes. You can use as textile coloration, food coloration, and others. But here we just focus on how to make pH indicators, yeah, to help you when you are not provided by your school probably, not having the synthetic pH indicators. Yeah. So here the soft skill that you can prepare from now, and then you can develop it, and then use that for your next or in your future. Yeah. Have you ever heard about anthocyanins before? Yes?
Sure. I haven't heard that anthocyanins before.
No problem. Anyone else? Yes, please.
Yes, I ever heard the anthocyanins before, but I understand
Anthocyanins are common that give color in fruit and vegetable.
That's correct. Anyone else would like to give another source for anthocyanins? Yes, please.
Anthocyanins not only found in fruit and vegetable. Anthocyanins can also be found in flowers, for example.
Yeah, that's really good explanation. Thank you very much. So, what are anthocyanins? Anthocyanins derives from Greek word. Yeah, it means anthos, yeah, which means flowers, and kyanos, which means dark blue. So together, to put together, anthocyanins means flower with dark blue color. Yeah. So to define what are anthocyanins, yeah, anthocyanins are the class of flavonoid. Yeah. Polyphenols. Yeah. And then these are natural water-soluble colored compounds and responsible, yeah, as has already been mentioned, yeah, for most red, blue, purple colors in fruits, flowers, vegetables, yeah, in some plants. Okay, there are 6 class, yeah, of the anthocyanins, that the major ones. The most found in nature, they are L-arginine, cyanidin, delphinidin, peonidin, quercetin, and maltidin. That's the explanation about the structural transformation of anthocyanins. Any questions? Yes, please.
Yes, I have a question. How to extract anthocyanin from natural products to be used as pH indicator?
Thank you very much for the questions. To answer your questions, I would like to bring back the previous slides. Yeah, we have already defined that anthocyanins are water-soluble compounds. So from that definition, what do you think of solvent that we can use to extract anthocyanins?
Water.
That's correct. So we can use water to extract anthocyanins, but we can also use another solvent to extract it. The disadvantages, yeah, when we use other solvents, yeah, so we can extract all of the chemicals, yeah. But if you use water, we can only extract the water-soluble compounds. Yeah, it means we reduce the complexity of the extract itself. Okay, so we have already discussed about the theory, yeah, about the acid base and then how to make pH indicators, yeah, based on the anthocyanins natural product. So after this, we will do the experiments in the lab. So before we go to laboratory to do some practicum, yeah, by extracting the anthocyanins from natural products, and then we will test the extract into the solutions, yeah, and then we will also examine, yeah, or determine the maximum wavelength of anthocyanin at different pHs. Yeah, and then before that, I would like to make a group, yeah, of 5. So there are 3 groups, yeah. There are 15 students here. So each group will consist of 5 people, yeah. To make it easy, probably please count 1, 2, 3, yeah, and then another person will continue the number. Yeah, start from you.
1,
2,
3.
1, 2,
3.
1.
2, 3, 1, 2, 3, 1, 2, 3.
Okay, thank you very much. For each number, please, please move into your group, yeah, based on your number, yeah. Please, group 1 over here, group 2 in the middle, and then group 3 over there. Yeah, so we have group 1, group 2, and group 3. Yeah, so each group should have different sources for the anthocyanins. So start with group 1.
We are already discussed and we are decided to use butterfly pea flowers or as known as bunga telang, and we are going to extract this.
Bunga telang or butterfly pea flowers. Thank you very much. Group 2.
Group 2 will choose berry sweet.
Thank you very much. For the last but not the least, group 3.
We are from group 3, have already discussed to use hibiscus flower.
Thank you very much. Yeah, so we have already done the practicum in the laboratory. Yeah, so you have now experienced how to make pH indicators, yeah, from natural products, and then you know how to test the extract into different solutions, yeah, with different pHs. And then you have already experienced how to use UV spectrophotometer to measure the maximum wavelength, yeah, of each solution at different pHs. Now we will start practicum in the laboratory. Yeah, so we have already discussed about the theory of acid-base and then anthocyanins, and then how to use anthocyanin as pH indicators. Now we are going to practice, yeah, how to make our own pH indicators, yeah, by using selected natural products that you have already discussed in your group. Okay, group 1, can you show your sample?
Butterfly pea flower or salad.
Okay, thank you very much. Group 2.
This is berry sweet.
Okay, cool. Group 3.
This is hibiscus flower.
Okay. So as we have already discussed before, yeah, the first step we need to extract the anthocyanins from the natural product, yeah, that you have already selected, yeah. So you use water in this case, using hot water, yeah, around 60 degrees Celsius, and then you will extract that for a certain time, yeah, 30 minutes probably is enough, and then you will use the extract to test the pH of the solution. Yeah, ranging from pH 1 to pH 12. Yeah, after that you analyze the solution using UV spectrophotometer to determine the absorbance and the maximum wavelength of the solution at different pHs. Okay, if you have any questions, you can start to work on the pH indicator now. Yeah, so we have already done the practicum in the laboratory. Yeah, so you have now experienced how to make pH detectors, yeah, from natural products, and then you know how to test the extract into different solutions, yeah, with different pHs. And then you have already experienced how to use UV spectrophotometer to measure the maximum wavelength, yeah, of each solution at different pHs. Now I would like to give the chance for each group to present what they have already found in the lab. So we will start with group 2. Are you ready to present?
Yes, sir.
Okay, good morning everybody. We are here from the group 2. We'll explain about our findings about pH indicator. So, yes, please, Rahman.
Okay, so firstly, we extract the anthocyanin from berry fruits using water at 60 degrees Celsius and a cycle of time. And then we put the extract to each solution to have different range pH from 1 to 12. And then,
Okay, after Rahman explains, I will continue. This solution range from 1 to 12 will be determined using instrument called UV spectrophotometer. In this, we put the solution into cuvette. Yes, it's chamber, the little chamber one. It is inserted to the tool, to the instrument, and then we operate the computers to determine the wavelength from 360 to 710 nanometers to determine the color. As you can see here, the results are shown as the pH 1, 2, 3, or the first 3 pHs. We can see that the wavelength or the peak or the maximum observance is occurred at around 520 nanometers. And as the color progresses, it is the more wavelength it is used to make it the maximum observance. For the 4, 5, it will be around 550. After that, and so on, and it will be the last one, 60 to pH 12. It will become at 660. About it, we can see that there is an influence by the compounds, the coloring compounds to the pH. For example, for the first 3 pHs from 1 to 3, we can see that the dominant compound is the flavylium cationic ions, and then as the color progresses, or as the maximum observance shifts to the right, it will become hemiketal. Hemiketal is the colorless substance, and then it will become quinonoid. It is colored as purple, and then the next is chalcone. It is basically yellow. It is yellow. So that's all from everybody. Thank you very much.
Thank you very much, Group 2. Give applause.